Hi guys, welcome back to Data Every Day. Today we're looking at a data set of bank marketing campaigns, which if you look at it is basically it's the telemarketing results from a bank in Portugal, and each client or potential client was some data was collected from them, and then at the end they either chose to subscribe to a term deposit or not. So either they deposited money or they did not, and that's what we'll be trying to predict. So let's hop into the notebook. We have NumPy and Pandas for working with the data. For pre-processing, we're going to use the standard scalar and train test split function from sklearn, and we'll use TensorFlow to construct our model. For evaluating the model's performance, we're going to use the classification report and confusion matrix from sklearn.metrics. Alright, so let's go ahead and load in the data using pandas.readcsv. So we can get the CSV file path over here, paste it in, and take a look. First thing we see, well, we have the wrong delimiter on here. So you can see there it's actually delimited by semicolons. So let's go in and change the delimiter to semicolon. And then we take a look. Here's our actual data set. We have 21 columns. The limit for how many columns Pandas will display at once is 20. That's why we have this ... here. So let's just get that extra column by going to the console and typing pandas.setOption max columns to none. And so now if we reload the data set, we can see all of the columns at once. Alright, so here's what we're trying to predict, and everything else is going to be used as data. Just from looking, it doesn't seem like there's any useless columns. They can all be used to help predict. Let's get a little information on the data set. That looks good. There don't seem to be any null values in the data set. We can confirm this by checking data.isNA.sum. So data.isNA is just a data frame that contains true or false based on if there's a missing value there. And we sum across the rows to get the number of missing values in each column. And then we sum again across the columns to get the total number of missing values in the data set. And we have 0. Alright, so we can just start encoding. Let's encode the labels first. So if we look at, I believe the column is called Y, that's what we're trying to predict. It should be yes or no values. When we look at the unique values in that, it's no or yes. So what I want to do is apply a function to it that's going to take in some y value, and we're going to turn it into 1 if y equals yes, and otherwise return it to 0. Now you'll see it has been encoded as 0s or 1s in the place of before it was nos and yeses. So that will be our new y column. And that's it. That's all we have to do for encoding the labels. Let's now encode the categorical features. There's a very nifty function that Pandas comes with called selectDtypes, which allows you to enter a data type and get all the columns that have the data type. So these are all the object columns, or in other words, all our categorical columns. There are no Boolean columns here, so object will capture anything that is categorical. And you can see many of these are going to be one-hot encoded. But we want to get a good idea of how many unique values are in each category. So what I'm going to do is create a dictionary. It's going to map a column to the length of the unique values in that column. So data subcolumn.unique, and then take the length, and we're going to map the column name to the length. And that's for every column in data.selectDtypes object.columns. So for each one of these categorical columns, we're getting the number of unique values in the column. And we can see this is a very manageable number. So what I'm going to do is actually now list all the unique values for each for each one. So I'll just copy this, and instead of getting the length, I'll just get a list of it. And now you can see each unique value in each column. So with this, well, actually there's something I noticed, that we have this unknown value in many of the columns, and that seems to be a missing value. So when we saw that there were no missing values earlier, that wasn't entirely true. They've just been encoded as unknown. So what we should do is replace data.replace unknown with numpy.nan. Alright, now let's take a look at the missing values. Before we get back to encoding, let's just deal with these missing values or figure out how we're going to deal with them. So I summed once to get the number of missing values in each column, and you can see there are a few columns here that have some missing values. Now, we're going to be doing these sort of in parallel, because the good thing about nominal features is that when you one-hot encode them, it automatically takes care of missing values, because the one-hot columns will have all zeros if it's a missing entry. But let's see. So we want to sort of sort these columns into different categories. So why don't I'll grab this again, and I'll just paste it down here. I just want that for reference. And then I'm going to make 3 categories: nominal features, ordinal features, and binary features. Alright, and let's start loading them in one at a time. So job is clearly nominal. There's no order between these values. So let's put job in there. Marital status, also nominal. There's no order between these. Education. You could say there's an order here, but the issue with that is it's not so clear. For example, does university degree come after basic 9-year or before basic 4-year? So because that's not very clear, the ordering of it, we're going to encode it as a nominal feature as well. So education. Default. So now these are some binary columns. They just have 2 values. And binary columns are easy because you just set one of the values to 1 and the other to 0. So let's load in these 2 binary columns. Housing as well. Loan, also binary. And contact, also binary. Month is ordinal, right? Because there's an ordering of the months, and you can use this feature to sort of get a sense of the temperature, things like humidity. I mean, there's just a lot of information encoded in the month. If we have a low value, which would be around January, February, we can know that it's cold in wintertime, and a high value, also cold, but medium value would be about, it would be warm. It would be during the summer. So month will be ordinal. And the last one, no, 2 more. Day of the week. So you could also say this is ordinal, but the thing is, there are so few values in here, and each one is sort of independent of the others. It's certainly not a continuous variable. There's no such thing as halfway between Monday and Tuesday. So it might make more sense to just encode this as a nominal feature, but this is really preference. I'm going to encode it as a nominal feature. That seems to make sense for me. And then the last one, P outcome, we can consider this nominal because non-existent is a valid, is valid. I wouldn't really consider that as a missing value. Maybe we could, but I'll just keep that in and say it's a nominal feature. Alright, so here's our features, and now what we want to do is write some functions to deal with these features. Actually, I probably should keep this here for now. So let's create 3 functions. One will be one-hot encode. One will be ordinal encode. And one will be binary encode. So we have to consider if we're dealing with missing values when writing these. For one-hot encoding, we don't have to worry. If there's missing values, it's perfectly fine. Like I said, all the one-hot columns will just have zeros for a missing training example. Alright, so let's start by creating a copy. Well, actually, I have to pass in some parameters here. It's going to take in a data frame, a list of columns, and a list of prefixes. Prefixes to put on the one-hot columns. So let's start by creating a copy of our data frame. And then for each column and prefix, in zip of columns prefixes, so zip will pair up the 2 lists element-wise into tuples, which we can then iterate through 2 at a time, accessing column and prefix at the same time. And what we'll do is create some dummies. So this is Pandas Getdummies, and this is what creates the actual one-hot columns. So if we just test out this function, if I wanted to get the dummies for a given column, let's say job. Yeah, job's fine. It looks like this. Every unique value from job, right? These were the unique values. They've now been turned into their own columns, and for a given example, we have a 1 in the column that had that value originally. So if we look at the data, example 0 had housemaid as job. So if we look here, there's a 1 for housemaid and a 0 for all the others. And you'll notice that missing values have been encoded properly. I don't think we have any right here, but if we did have a missing value, we just have all zeros for a given example. So that deals with them nicely. So I should also say we can include a prefix here. Let's say job. That will just append a little prefix to the beginning of each column name to prevent any so that we always know which column these one-hot columns originally came from. So what I'm doing here, I'm going to get the dummies for a given column using the prefix that goes along with it, right? Because we're iterating column prefix at the same time. And we haven't written up the prefixes yet, but we will. Then let's concatenate using pandas.concat the original data frame and the new dummies columns side by side, so axis 1. And then we're going to drop the original column from which we created the dummies, because it's no longer useful. And at the end we'll return df. So there's our one-hot encode function. For ordinal encode, we need to specify an ordering for each column. So it's going to take in a data frame, a list of columns, and I could just code this simply instead of zipping them together. Because we only have one ordinal feature, why not? I'll just do both. I'll code a more general function that can be used on a list of columns. So we're going to specify some columns and some orderings that will match up with the columns. And we'll start again by creating a copy of our data frame. And then for, like before, column, but this time ordering instead of prefix. In zip, columns, orderings. So ordering is going to be a list. We're going to have a column name and a list. And what we're going to do is take the column, and we're going to apply a lambda function to it. It's going to take in some x, and it's going to return ordering.index of x. So if we specify an ordering, which is a list, right, one of these, we can index a given value in the list to get the integer associated with it. That is a convenient way to turn an ordinal feature into a numerical feature. Okay, So, last thing, I think this is it for this one. Return df. And then last thing is binary encode, which will take in, we'll take in a data frame, a list of columns, and a list of positive values. So we're going to start by creating a copy, and then let me just copy this. We're iterating again, 2 at a time, but instead of orderings, we're going to be using positive values. So we're going to apply a similar transformation as before, but instead of doing ordering.index, we're going to do similar to what we did to the labels earlier. X will become 1 if X is positive value, and otherwise will become 0. So this will just change X to either 1 or 0, depending on if X equals the positive value that we specify. And at the end, we'll have a numerical column with 1s and 0s. So return df, and there are our 3 functions. Now let's construct some prefixes for the ordinal features, some orderings for the ordinal features. So these are for nominal, these are for ordinal, and then some positive values for the binary features. Alright, so prefixes. We just have to make sure that they match up element by element, because we're zipping them together. So how about J for job, M for marital, E for education, D for day of the week, and P for P outcome. Orderings, this should have a list inside, because each ordering is a list. So let's do this, and then we'll paste in January, February, March. It's just going to go through the whole months. So I'm just going to copy it because I don't want to type it all out. It's just every month, and you'll see that even though in the actual values we don't have all the months there. Like I don't think January is here. We're still going to include all of them because we want them to be on a sort of evenly spaced scale. Okay, and then positive values. So we need 1 positive value for each binary feature. And so we have to look at this now. For default, so these are our 4 binary features. For default, the positive value is yes. For housing, the positive value is yes. For loan, the positive value is yes. And for contact, we can choose anything. Cellular, but we'll make cellular the positive value. So we just have to make sure these also map up element-wise to the binary features. So it's yes for default, yes for housing, yes for loan, and cellular for contact. Alright, and now let's run this. We can remove that, and we can apply the encodings. Oh, one more thing I actually forgot about. This is going to bring us some issues, because if we look at the missing values here, job is nominal, marital is nominal, education is nominal. So we don't have to worry about the missing values for that. Like I said, the one hot will take care of it. But default, housing, and loan have missing values, and those are binary features. And we have to deal with it a little differently in that case. We want to make sure that when we're encoding the binary features, we're not overwriting missing values with 0, which is what this will do. So what I'll do, instead of changing it to 0 if it's not the positive value, I'm going to just keep it the same way. Keep it as x. And then I'm going to apply a second transformation right under it that is going to change it to 0 if string of x is not equal to nan. So this is saying, let's first check if it's equal to the positive value, and we'll change all positive values to 1 and keep all the rest the same. And then we'll check if we don't have a missing value, and we'll change it to 0 if we don't have a missing value. And if we do have a missing value, we'll keep it the same, so it'll still be missing. And that will solve the problem. We might have to do something with the ordinal encoding in that. If we did have missing values in an ordinal column, it'd be as simple as saying if string of x is not equal to nan else x, right? But we don't have to worry about that because we don't have missing values in the ordinal columns. So now let's run, we get our prefixes, orderings, positive values. Now let's apply the encodings. So first let's do the one-hot encoding. This is going to take in the data frame, a list of columns, which will just be nominal features, and a list of prefixes, which will just be prefixes. Okay. Then we'll do ordinal encoding, pass in the data frame, list of columns, which will be ordinal features, even though there's just one in there. A list of orderings, which will be orderings, even though there's just one in there. And then for our binary features, we'll use binary encode, takes in the data frame, the columns, which will be binary features, and positive values, which will just be positive values. Okay, I'm going to run this. What is this? Did I? Oh, I didn't put a comma. Whoops. Okay, let's rerun the whole notebook then. Alright, and take a look at the data. You'll notice we now have 45 columns, and everything is numerical. And we still have some missing values, so let's deal with those now. So filling missing values. It's not that hard. Let's just we'll keep this one up here, and then we'll check data.isInA. IsInA just gives us this true or false. If there's a missing value there, it'll be true. So let's sum across the rows to get the total number of missing values in each column, like we did before. And we can see that there's 3 left: default, housing, and loan. And right now, after they've been encoded, they are numerical, right? And so what we'll do is fill it with the mean. We'll fill these missing values with the means of the columns. So what we can just iterate through, we can say for column in, and then I'm just going to go and process this a little. Okay, so for column in default, housing, and loan, data subcolumn equals data subcolumn dot fill NA with data subcolumn dot mean. And we could use the mode here since it's binary, but I actually, if you look at it, the mean is 0 for all of them, so it doesn't matter. So this will fill NA just fills missing values with a given value, and the value we're giving it is the mean of the column. Alright, so now let's just print out remaining missing values, and we will get the sum over both the rows and columns, and we have 0. Then let's also print out remaining non-numeric columns, and we'll print out the length of data.selectDtypes, pass in object dot columns. So basically the number of columns that have object data type, and 0. So our data is fully ready for splitting and scaling. Alright, so this is a nice clean data set now, no missing values, no worries, no more categorical variables, everything is numerical form and ready to be scaled. So let's split it into x and y. Y is what we're trying to predict, and the column we're looking for here is y. So y equals data sub y. We'll make a deep copy of it. Then x is going to be data.drop y, because we're going to use all the other data to predict y. And I'll make a copy of that as well. And then I'm going to create a scalar object. This is a standard scalar from sklearn, which will just allow us to, we'll fit the scalar to the data, and then we'll transform x according to the fit. And so it's going to give each column mean 0 and univariance, so that all the columns take on a similar range of values, which will just make it a lot easier for our model to work with. So we'll run that. Then we have xtrain, xtest, ytrain, ytest equals train test split, x, y, give it a train size of 70%, and include a random state so that we can reproduce the results. Additionally, before we move on further, I actually want to seed TensorFlow. So TensorFlow.random.setSeed, and we can give it any value. Let's just use 100. This will ensure that all of the random number generation from TensorFlow is reproducible. So if anyone else wants to get the same results as me, you just load up the notebook, use the same seed that I did, and there shouldn't be a problem. And that's the same thing that's going on here, because this function actually shuffles the data as well as splitting it. Okay. Now, modeling and training. So we're just going to use a very simple standard neural network for this. First, let's get a sense of the class distribution. So I'm going to print out the number of positive examples, and I'll format a string here. I'm going to put in y.sum. So, y is it's a column of ones and zeros, a series of ones and zeros. So if we sum, we'll get the total number of ones, right? Because all the zeros get added up, all the ones get added up. So this will show us. Oh, whoops! This will show us the total number of positive examples. So these are the number of times a customer made a deposit in the bank. And then we're going to do negative examples as well. So this value will be the length of y minus y.sum. That will just be the total number of zeros. And then let's also print, I'll just put a new line, the class distribution. And I want to display it to one decimal place, 1f, and slash, and another value displayed to one decimal place. I'm going to format this with the mean of y. So if you think about it, mean is just the sum divided by the length, so that will be the percentage of ones in y. And let's multiply it by 100 so we can get it in percentage form. And then for the second value here, we're going to do 1 minus the mean. Times 100. Okay. And yeah, let me put percent signs at the end. So we have 11.3% to 88.7%. So there's a substantial number more examples that are negative than there are positive. It makes sense because the telemarketing is not known to be so effective, so it probably only works on probably only a small number of potential customers actually make deposits. Alright, so let's create an input. So this is our model now, and we're starting off with an input layer. The vector we want to pass in is going to be all of our features. So the shape is going to be x.shape sub 1, a vector of length x.shape sub 1. So x.shape is number of examples by number of features, so 44 is what's getting plugged into here. Okay, let me close this out. Then we'll create two hidden layers, tf.keras.layers.dense, with 64 activations each, and ReLU activation function. We'll pass in inputs, and then to the second one we'll just pass in x. Then our output layer will also be a dense layer, but with only one activation, since this is binary classification. And we'll use a sigmoid activation function to give this one value a value between 0 and 1. And so this will serve as the probability that a customer makes a deposit. Then we'll create a model, tf.keras.model, pass in the inputs and outputs, and we'll compile the model. Let's give it an atom optimizer. For loss, we'll use binary cross entropy for a binary classification. And metrics, let's use two metrics. We'll use accuracy, but then also because we have such a skewed class distribution, we're going to use AUC as well. tf.keras.metrics.auc. Give it a name, AUC. And so this is much more, it's much better at giving a result like within each class. What I mean is it takes into account the model's performance within the positive class but also within the negative class, whereas accuracy only deals with how many you got correct. So in this case we have 88% negative, so if our model guessed negative all the time we'd get an accuracy of 88%, but if you think about it, our model's actually not doing the job at all. So that's why accuracy is not so great, especially in cases of skewed classes. Alright, so we'll create a batch size. Let's do 32. And I'll train for a bunch of epochs because I want to use this early stopping callback. So I'm going to store the model's fit history in history. And we're going to train on the train set, xtrain, ytrain. And let's give it a validation split of 20%. So 20% of the training set will be used for validation. Then batch size, we can do as batch size. And epochs we'll do as epochs. And then I want to specify this callback. It's tf.keras.callbacks.early stopping. And we're going to monitor. So this is the value we want to be watching, the validation loss. And so when we notice that the validation loss stops improving for a certain number of epochs given by patients, let's say 3 epochs. So when we see the validation loss is no longer improving after 3 epochs, we're going to stop the training and we're going to restore the weights from the best epoch. So restore best weights equals true. And we'll go ahead and start training. And this should not take all 100 epochs. It should train until the validation loss reaches a minimum, and then when it starts going back up, it'll stop and restore the best weights. And it looks like it already did that. So let's get some results. First, let's just evaluate the model on the test set. And we have an accuracy of 90% and an AUC of 0.92. So this AUC being high is very good. This means that the model's able to distinguish between the classes even though we have this skew here. So let's also get a confusion matrix and a classification report. So I'm going to make yTrue be just a NumPy array of yTest. So the answers to the test questions you could think of. And then yPred will be model.predict xtest. But this returns the probability values given by the single sigmoid activated output. So we have to turn this into a logical array, checking if it's greater than 0.5 to get 1s and 0s. This will actually be true and false. So let's make it into a NumPy array with the data type numpy.int. So it turns true and false into integers. And then lastly, this actually returns a 2-dimensional array, model.predict does. So let's squeeze it down to 1 dimension so it lines up with our yTrue. Okay. and then we're going to print out confusion matrix, new line, and then this is the confusion matrix from sklearn. You just have to pass in yTrue and ypred. And you can see, so these will be true negatives, true positives. So along these axes is the actual values. So if it's in the top row, it's actually negative. If it's in the bottom row, it's actually positive. And the columns are our predictions. So if it's in the first column, we predicted it to be negative, and if it's in the second column, we predicted it to be positive. So these are values we predicted positive, but were actually negative, and these were values we predicted negative, but were actually positive. And you can see we predicted more negative than. Sorry, let me explain this. Out of the positive class, we predicted more of them to be negative than we did to be positive. So let's get a classification report. This will clear things up a little. I'm just going to put 2 new lines and then the classification report, which is also from sklearn. Pass in yTrue and ypred. And we can see precision and recall and f-score. So the f-score is a good way of understanding performance within a class, and you can see that our performance in the positive class is not so great. It's better. We have a really good performance in the negative class, but that's understandable because we have so many more values in the negative class. So precision is out of all the values we predicted a certain way, how many did we get right? And recall is out of all the actual values of a certain type, how many did we predict that type? So you can see both in the negative class we have very good values, in the positive class not so much. It just looks like overall our models perform much better in the overrepresented class. So a few things we could do here would be to add some class weights to try to even it out. But that will probably lower our overall accuracy and lower our overall AUC. Maybe not the AUC, I'm not sure. It depends. But our accuracy will probably go down at the expense of better performance within the positive class. I'm not going to do that today. I'm going to leave it as it is. Even though this is not perfect, there's a lot that can be done to improve it. But I think that was a good place to stop. Thank you so much for watching. I hope you enjoyed today's video. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.